All right, our topic today is still dot product related. We're looking at some more applications of the dot product. Mostly just two ideas actually. One of them we can do relatively quickly, and the other one is quite a bit more significant. So our first application is the idea of an angle. So can we actually figure out what the angle is between two vectors? And remember, we've done this before. It was a while back in the first unit. We had a couple of vectors and we used some trigonometry to get an angle. We want to try and do this one a little bit more easily, and that's going to be based on the dot product. Okay, now remember, we have two ways that we've talked about for the dot product. We can calculate the dot product geometrically. At least we usually thought of this as geometrically. Right? We can do that. Or we can also do this. Two different ways of calculating the dot product. Both work. So what's interesting is if I'm given two Cartesian vectors, like I am here, we should be able to calculate the magnitude of A and the magnitude of B. Right? We could do that. We can calculate, so we can calculate that, we can calculate that, and we can calculate that. Which means the only thing that's missing is cos theta, which will allow us to get the angle. So basically what we're doing is we're putting these two formulas together. Oops. And we're saying this is true. Okay. That's our formula that we're going to basically use here. So we need to do a little bit of work on the side. We need to know the magnitude of A. Magnitude of A is the square root of 3 squared plus 4 squared. So the magnitude of A is just 5. Magnitude of B, is square root of 50. Square root of 50 is kind of special, though. It can reduce. You can write that as the square root of 25 times square root of 2, or just 5 root 2. And that's going to actually help for a question that we're going to do in a minute. So that works out nicely. We also need A dot B, right? So actually calculating the dot product using our A1, B1, A2, B2. So that's 3 times 7 plus 4 times 1, which is 25. So that's all of our work on the side. I guess I've made a bit of a mess of things now for sake of board space. I'm going to use this green formula again now, right? The magnitude of A was 5. The magnitude of B was 5 root 2 times cos theta. And the dot product, which I just calculated, was 25. And we're trying to find cos theta. So cos theta, 25 on the top. I'll divide by everything that was on the left there. 5 times 5 root 2, which is just 25 root 2. 25's cancel. And you get 1 over root 2, which is actually one of our special angles. So you could use your calculator, right, and do cos inverse, but you might actually remember that's one of the special ones. Cos theta is 45 degrees. Or if you're still in advanced functions mode, theta is pi over 4, right, if you're remembering your special angles that way. And this is, don't get me wrong, I set this up so that we'd get a nice angle of 45 degrees, right? That doesn't happen too often. If I pick any two random vectors, you're not going to get a nice angle that comes out to exactly 45. That was just a special case here. So here's our first example of what we can do to actually calculate the angle between two vectors, two Cartesian vectors. We can get it that way. The second idea is an idea called a projection, and we're going to spend the rest of the time looking at this. This can be a tough one. But what we're going to try and do is we're going to try and generate a formula that's going to allow us to calculate it relatively easy. That's what we'll do by the end of the lesson, at least. So a projection, it says let vector A equal OA. So we can see vector OA in this picture. And vector B be some other vector. So that's that horizontal looking vector there. And some angle theta in between them. Let N be some point on this line segment or this vector OB such that the line that goes straight down from A to N is perpendicular with vector OB. So really we're putting point N somewhere on that line so that we're making a right angle triangle. That's all. We're trying to figure out where point N would go so we get a right angle. Well, when we find point N, we call this vector right here from O to N the projection of vector A onto vector B. So the description I use is this idea of a shadow. We're sort of imagining, and forgive me, I'm waving my hands around like this. We're imagining this vector here. We're seeing the shadow on the ground of vector A onto vector B. So we're interested in trying to find that green vector, and we're calling that the projection of vector A onto vector B. You can see the way we've written it here. We're using a little subscript, kind of like how you'd write a logarithm, right? It's the projection of vector A onto vector B. So we're going to try and first just calculate it. We're actually using the same two vectors that we used a second ago. So vector A and vector B, still the 3, 4, and the 7, 1. That's just going to save us a little bit of time with some calculations. We can draw this. Here's vector A here. Here's vector B. And we're trying to get the projection of vector A onto vector B. So I need a line going straight down. It's going to meet at a right angle. And we're trying to get that vector right there. That is the projection of vector A onto vector B. So that's the goal of this question: is can we come up with components for that green vector? Now, something to keep in mind: we can see vector B, right? We know that its components are 7, 1, and this green vector is collinear to it. It's in the same direction. So this will certainly be true. The projection of vector A onto vector B has to be some multiple of vector B, right? In fact, it looks like in this case it's smaller, right? N has to be some number between 0 and 1. That's not always the case, but in this case, at least we can see that N's got to be between 0 and 1. It's some number that's going to scale vector B up or down. So it's not a real quick process to get it. What we need to do is we first are going to try and figure out the magnitude of that particular green vector, so just how big it is. And as it turns out, that's not hard to do because of the work that we've just finished doing. Let me back up a minute. When we had those two vectors and we found the angle between them, right, we know that the angle between them is 45 degrees. That's good. And we also found out that the magnitude of vector A was 5. So I'm going to put that into this picture. It's going to be tight. I'll squeeze it in there. That's 45 degrees. And vector A had a magnitude of 5. So in that picture, we're trying to find the length of the magnitude, the length of that green vector. I'm just going to call it x for a minute, okay, just so it's a little bit easier to do the math. We're trying to find vector x, or the magnitude, the length of vector x, and you have a right angle triangle, so we can use, I think, just the cos ratio here. If I do cos of 45, cos of that angle, is equal to the adjacent side, which we called x, divided by the hypotenuse, which was 5. So x is just 5 cos 45. Okay, that's the length of it. And I can actually simplify that a little. I'm going to still try and use a whole bunch of exact values. Cos 45 is 1 over root 2. Mr. Vandenberg often wrote that as, for cos 45, I like to write it as 1 over root 2. He often wrote it as root 2 over 2. They're the same number, okay, same number. I actually like this better. So I'm going to leave it as 1 over root 2. It's a little bit simpler. So the length of x is 5 over root 2. That's not as long as vector b. It's not as long as vector b. But I'm going to use that length to try and scale vector b down, right? We said here that the projection was going to be some multiple of vector b. I can use this number, this new magnitude, to help with that. The easiest way to do it is to get a unit vector in the direction of vector b. And we did that, I think it was yesterday, wasn't it? The formula for a unit vector was 1 divided by the magnitude of the vector times the vector. Right? That would give us a unit vector in the same direction. And we calculated this too in the last example, right? The magnitude of vector b was the root 50, which we reduced to 1 over 5 root 2. So that there, vector u, is a unit vector. It has a magnitude of 1 in the direction of vector b. So it's in there too. I can maybe put it in. It would be like that. Okay? It has a magnitude of 1. Now, I want the projection to have a magnitude of that 5 over root 2. So all we need to do is we need to take that 5 over root 2 and multiply it by the unit vector that we had. That'll scale it up, right? If the unit vector has a magnitude of 1, then if I multiply it by 5 over root 2, it will then have the magnitude of 5 over root 2, which is what I want. So 5 over root 2 times our unit vector, which looks like that. And again, I set this up to work out really nicely. This doesn't happen very often, but those 5s, 5 on top, 5 on the bottom, that'll cancel. And then the root 2 times the root 2 is just a 2. So in this example, our projection is actually exactly half of vector b, okay? Which we could write, because vector b was 7, 1. Yep. So the projection is 7 over 2, 1/2. Now there's a lot of work there to do that, especially when you consider the work that I didn't even show on this page, right? If we go back, we had to do all of this stuff too. We needed both of those magnitudes. We needed to figure out the angle. There's quite a lot of work required to come up with that particular answer. So what we want to try and do next is come up with a formula for calculating the projection more easily. It actually works out really simply in the end. It's just a little formula that we remember. And that's what this is all about now. We're going to try and come up with this formula. We're going to follow exactly the same steps that we just did, but we're going to do it all in general instead. So trying to figure out the projection. The first thing that we did was we figured out the magnitude of the particular projection. Forgive me, I'm going to jump back and forth a little bit here. Right, the first thing that we did was find the magnitude of that little green vector. And the way we did that was we used the cos ratio. And that's what we see here. So if we do cos of theta, here's theta. Cos of theta is the adjacent vector ON divided by the hypotenuse, which is the magnitude of vector A. And that's what you see here. So cos of theta is the adjacent divided by the hypotenuse. And we rearranged that. We multiplied the A up here. And so we ended up with a little formula for the magnitude of our particular projection. You can calculate the magnitude of the projection by going magnitude of vector A times cos of the angle in between. Remember, that still isn't easy to calculate unless you're given all of that information. Okay, but we're going to use that. So we now have a formula for the magnitude of the projection. What we did from there was we multiplied that magnitude by the unit vector in the direction of b. Right? We calculated that unit vector, and then we multiplied the unit vector by the magnitude of the projection, and that's what you see here. So in order to calculate the projection, what we did was we took the magnitude of the projection and multiplied it by the unit vector. So in the next line, I've made that first substitution. We just said that the magnitude of the projection was the magnitude of vector A times cos theta, right? We just found that. And then after that, all I've done is I've replaced vector u. I've called the unit vector vector u. And what's good here is that we've already got a formula for vector u, right? To get that unit vector, we calculate it like so. Any unit vector in the direction of a particular vector is 1 over the magnitude times the vector. So I'm going to make that substitution. I'm going to replace this here. So our formula for the projection is now magnitude of A cos theta times that unit vector, which is 1 over the magnitude of B times vector B. And that's good, right? That's better. We're going to try and simplify it a little bit more still. And that's what we see here. So we have a pretty good formula already, but it's only really good if we have geometric vectors, and that's not what we're focusing on in this unit. We're focusing on Cartesian vectors. So what we're going to do, we're using that information about the dot product that similar to what we talked about when we did the angle question at the beginning. If A dot B is equal to the magnitude of A magnitude of B cos theta, I can rearrange that for cos theta. And when I rearrange it, I'm going to take this expression and I'm going to substitute it in for cos theta. So it makes things look worse at first. Right? The projection is now the magnitude of A, looking at this line here, magnitude of A times A dot B over magnitude of A times magnitude of B times that unit vector still, 1 over the magnitude of B times vector B. So it looks ugly, but if you look at what happens, you've got a vector A on the top and a vector A on the bottom, so those just cancel. And then you've got the magnitude of B and the magnitude of B again, so we can write that as the magnitude of B all squared. And that actually works out really nicely, because if you think about magnitudes, we calculate the magnitude of a vector using Pythagorean theorem, right? We have to take the square root. Well, now that we square it, that's going to take away the square root. That leaves us with this. And this is a formula that we have to remember. Okay, you won't be given this, you just have to remember that as a formula for the projection. That's a relatively easy calculation now, and that's our last question. We'll do it on the next slide. To calculate the projection of vector A onto vector B, all you have to do is do A dot B, divide that by the magnitude of B squared, and use that as the scalar in front of vector B. Remember, right from the start, we said the projection of A onto B was going to be some scalar of vector B. It was going to be in the same direction. So what we're trying to do, we had to do this calculation to figure out what the particular multiple of vector B should be. All right. So I'll show you the example of how that works. I've just got the formula there on the right-hand side. Here's our new one. It's projection of F onto M. We're given vector F, we're given vector M. And can we calculate that projection? So aside things that we need to find, well, we need to find A dot B, or in this case, F dot M. And given Cartesian form, to do that, we just multiply the components together and add them up. That's just -1. So our dot product is -1. And we also needed the magnitude, oops, not vector B anymore. The formula said magnitude of vector B squared, right? That's the lowercase one there, the subscripted vector. Because in this case, it's projection of F onto M. So we need to get the magnitude of vector M squared. So the magnitude of vector m would be the square root of minus 3 squared plus 2 squared, right? That's just the magnitude of it. And then we square that. So the square root and the squared part disappears. And you're left with 9 plus 4, so just 13. So the magnitude of vector m is 13. Magnitude of vector m squared is 13, sorry. That's all of the work that we had to do on the side. So to find the projection now, we're doing f dot m over the magnitude of vector m squared times vector m. F dot m is a number, magnitude of vector m is a number. Vector m at the end is a vector. So minus 1 over 13 times vector m, which I suppose we could write this way. Vector m was minus 3, 2. So our final answer would be 3 over 13 minus 2 over 13. That's the projection. So because we know this formula now, that calculation becomes quite a bit more reasonable. Deriving the formula was tricky. Right? There's quite a bit there to deriving that formula again. Okay, so there's 2 examples of how we can use dot products. With what we're doing now, we'll still use, you probably wouldn't even believe me how much we're going to be able to use dot products when we get a little bit further on. But this will get us started. These are 2 very good uses of how to use the dot product in 2 dimensions. Next lesson, we're going to jump up to 3 dimensions. But everything that we've done so far still applies. So adding 3 dimensions is going to be, well, I think it's interesting, but it actually doesn't overcomplicate things too much. All of the work that we've done will still apply.